Chapter 5 in the abstract algebra series is operations on sets. And in problem number 1, we're going to take a look at a couple of important laws. They're called DeMorgan's laws. And DeMorgan's laws are used to simplify the complement of either the union of two sets or the intersection of two sets. And in problem number 1, we're actually going to apply it to both cases. So let's see what we have here. We're asked to simplify the complement of the union of these two sets. Well, if an element is not in the union of two sets, then it is not in either set. In other words, the element is not in the first set, and it's not in the second set. Because to say that X is not in one set or the other is equivalent to saying that it's not in both. Notice that the first portion here involves the complement of the intersection of two sets, and we can apply DeMorgan's law again for the intersection of two sets, for the complement of the intersection of two sets. And if we apply DeMorgan's laws, we get A complement union B. Because this is equivalent to saying that if X is not in the intersection of two sets, then X is not in one or the other. X is not in the intersection of two sets, therefore it is not in one or the other. And then of course I just brought down the intersection of C complement. Number 2, show that A union B is a subset of A union B union C. To do that, we would just let X be an element in A union B. And that implies that X is also an element of that set union C. Because union means one or the other or both. And we know that X is in A union B. Therefore, it is in the union of those two sets. And if I clear out parentheses, I have now shown that X is an element of A union B union C. And if every element in A union B is also, therefore every element that is in set A union B is also in A union B union C, which makes A union B a subset of A union B union C. Let's take a look at problem number 3. On problem number 3, we have two sets that are equal to one another. We have the set A not B is equal to the set B not A. Well, two sets are equal if they have exactly the same elements, the same set of elements. And A minus B, or A not B, I'm going to let that set be represented by the series of dots in the left crescent of the Venn diagram. All of these red dots are in A, but notice that they're not in B. In other words, they're not in the overlap area. And then I'm going to let these dots in the right crescent represent the elements that are in B not A. But we have to go back to the very beginning, because in the very beginning, we have this equal sign here, which claims that the two sets are equal to one another. That means that any element that I can find in A not B, I can also find the element in B not A. Again, any element that's in A not B can be found in B not A. And I could continue to do this for all of the elements in both sets. Well, if all of the elements in the left crescent over in here are also in the right crescent, then we have essentially the same set, which means A and B are equal to one another. Number 4. On number 4, we have 3 sets. We have A, B, and C. And A contains 3 elements, 1, 2, 3. B contains 4 elements, 2, 3, 4, 5. And C contains 1 element, and that's the number 1. And we're asked to take the union of two sets, sets A and B intersect C. If we start with B intersects C, if an element is in B intersects C, it means it has to be in both B and C. But C only contains the number 1, and notice that B does not contain the number 1, which means that the intersection of those two sets is the empty set. And what happens when you take the union of a set with the empty set? Well, you just get that set back. In other words, the union of A and the empty set would just be set A. Okay, let's take a look at number 5. Number 5 says that the math department currently has 20 students majoring in math. The physics department currently has 50 students who are physics majors. 7 students are majoring in both math and physics. So how many students are majoring in math and or physics? So let's see what we have here. Whenever I solve Venn diagram problems, I like to get the most bang for the buck that I can. So I start with the area that has the most overlap. Fortunately, we only have 2 circles here, and that makes it fairly simple. But notice we have 7 students who are majoring in both math and physics. Double majors. And we'll represent those 7 students here in the overlap. And let's go back again and take another look at the problem. So again, if we have 7 students who are in the overlap, then how many would we have in the left and right crescents? If we go back to the problem, we have 20 students majoring in math, and 7 of those are already represented by the heart symbols. And 20 minus 7 means that there are 13 in the left crescent, pure math majors. And then we have the 50 physics majors. And if you take 7 from the 50, that will leave you 43 students who are majoring in physics, but not in math. So how many total students do we have who are majoring in math and or physics? If we take the 13 in the left crescent and we add the 7 in the overlap and then the 43, that means we have 63 total students.